Hi guys, hope you're having a great day so far. We're going to continue chapter 14, which is rates of chemical reactions or chemical kinetics. So in order to understand why reactions happen fast or slow and their kinetics, we need to understand why reactions occur or how they occur. So if you remember from last year, we talked about collision theory, which says that particles have to collide in order for a chemical reaction to occur. Now, collisions happen all the time, but the reactions don't always occur. For example, if I have a match and I light it, well, what's happening here is that the oxygen particles in the air are reacting with the wood particles in the match. But if I don't strike the match, there's no reaction, even though gas particles, the oxygen particles in the air are constantly colliding with the wood, right? But no reaction is happening. Why? Because they're not effective collisions. In order for the collisions to be effective, I need to give it a little bit of activation energy. So I strike the match and then the reaction occurs. So in order for a collision to be effective, you have to meet two requirements. The first requirement is that the particles must collide with the correct orientation. So they need to collide with the correct orientation. They need to line up correctly so that the correct bonds in the reactants start breaking and the correct bonds in the product start forming. The other requirement is that they need to collide with enough kinetic energy to equal or surpass that activation energy barrier. So that's why when I strike the match, I'm giving it enough energy so that my collision would become effective. So again, two requirements: they must collide with the correct orientation and with enough kinetic energy. So I have a little animation here to show you. So here are two molecules. They are colliding, but not with enough kinetic energy, and so no reaction occurs. Next, they are going to collide again, but they are not colliding with the correct orientation, so no reaction occurs again. And now they're going to collide fast enough with the correct orientation, and that's when you get a chemical reaction. So correct orientation and enough kinetic energy is what you need. Now let's talk a little bit more about this activation energy and the collision that needs to have enough kinetic energy to surpass or equal that activation energy barrier. We're going to look at an exothermic reaction and also an endothermic reaction. Let's start with exo. And so this is your energy. This can be time, or it can also be reaction progress if you'd like. So the reactants have a certain amount of energy. In an exothermic reaction, energy is released from the system, and so my products have a lower amount of energy. So let's say products are right here. And remember that it doesn't go straight, it kind of goes through a hill and then goes back down. The difference in the potential energy of the reactants and the products, that's your delta H of reaction, which if it's exothermic, then it's negative. And from where the reactants are to the top of the hill, this is your transition state, if you remember. The transition state, also known as activated complex. Let's write that down. Activated complex. This is a complex structure kind of in between reactants and products. It's a structure where the bonds of the reactants are starting to break, the bonds of the products are starting to form. So in order to get to that transition state, basically these particles in the reactants are colliding, but if they don't have enough energy, they fall back down and reform the reactants. Collide, go back down, collide, go back down. If they collide with enough energy to reach that transition state, then that's when the reaction could occur. Once you reach that transition state, you can form the products, or possibly you can also go back and reform the reactants. And that happens with reversible reactions. We'll talk about that more next chapter. But for now, basically, these reactants need to collide with enough energy to reach that transition state. So the difference in energy between the reactants and the transition state, that is your activation energy, EA. So activation energy, I'm going to write it down here, is the activation energy This is the minimum energy required for reactants to react. Now, the higher the activation energy, the slower the reaction will occur. If you think about it, if these reactants need to collide with enough energy to reach this point, if the activation energy is really, really high, then very few of those collisions are going to reach that. And so very few of the collisions will actually result in a reaction. Very few of the collisions will be effective collisions. And so it's going to take a long time before we get a collision that is effective. If your activation energy barrier is pretty small, then it's pretty easy to surpass that and for an effective collision to occur and a chemical reaction to occur. And so what really determines the kinetics of a reaction is really that activation energy. The lower the activation energy, the faster the reaction. The higher the activation energy, the slower the reaction will be. Let's look at an endothermic reaction. So let's stay with the blue. So here are my reactants at a given amount of potential energy. Now in an endothermic reaction, my system absorbs energy. So if the system is going to absorb energy, then my products end up at a higher amount of potential energy. Again, it doesn't go straight. You have like a little hill, and then it goes down. The difference between the reactants and the products, oops, I went a little bit too far here. About there maybe. That's your delta H, and if it's endothermic, then it's positive. The top of the hill there, this is your activated complex or transition state. Between where the reactants are and that transition state, this is your activation energy. So again, that activation energy barrier is what you need to surpass in order to have an effective collision and have a reaction. And so this is part of why exothermic reactions are a little bit more favorable than an endothermic reactions. Usually the activation energy barrier, of course it depends on what the reaction is, but usually if you look at the reaction and its reverse, so going from reactants to products versus products to reactants, you will see that the activation energy is lower if it's an exothermic process versus an endothermic process going the other way. And that's why these usually happen a little bit faster. There are factors, of course, that affect how fast the reaction occurs. Activation energy is what decides it for sure, but you could do some things to help a reaction out. So these 4 factors are right here. First is temperature. So what happens if I increase the temperature? Well, if I increase the temperature, then my reactant particles are moving faster. And if they're moving faster, they're moving with higher kinetic energy. And so if they're moving with higher kinetic energy, more of these collisions are going to reach or surpass that activation energy barrier, and more of my collisions will be effective. So that's what this is saying here. The higher the temperature, the faster the rate. That's because at higher temperatures, particles will be moving faster, which will result in more collisions, but also more of those collisions will be effective because the particles have higher kinetic energy. And so more of them are likely to equal or exceed that activation energy barrier. So there's actually 2 reasons why temperature raises the rate of a reaction. First, because particles are moving faster, so there's more collisions, period. But also because more of those collisions will also exceed or equal that activation energy barrier, so more of them will be effective collisions. Next is concentration. So usually the higher the concentration of the reactants, the higher the speed of the reaction as well. The higher the concentration, the faster the rate. The reason is because if you have the same volume, but you have more particles in the same volume, then they're going to collide more. And so if you have more collisions, then you're probably going to have more effective collisions and it's going to happen faster. So higher concentration means that there are more particles in a given space, which increases the frequency of collisions, and therefore there will be more effective collisions. So remember, when you talk about rates, you need to talk about not just collisions, but effective collisions. That's the key there, effective collisions. Particle size and surface area. So if I have the same amount, but I break it up into smaller pieces. So for example, if I'm going to put something this amount versus I break it up into, smaller pieces. So same amount, but smaller pieces like this. Then the smaller pieces, the smaller particles have a higher surface area, and so more of them are exposed and able to collide. So you get faster collisions and faster effective collisions. So the smaller the particles, or the higher the surface area, like in this picture here, the faster the rate. If particles are smaller or have higher surface area, more particles are exposed to the surface and available to collide, and therefore there will be more effective collisions. And finally, the presence of a catalyst affects the rate of a reaction. The presence of a catalyst increases the reaction rate. Addition of a catalyst provides an alternative pathway with a lower activation energy. This means that more particle collisions will equal or exceed the new lower activation energy, so more of the collisions are effective and produce a reaction. So let's look at what that really means. What happens when you add a catalyst is that sometimes that changes the pathway of the reaction. So it changes what the transition state or activated complex looks like, and it makes it into something that is lower in energy. So now this is the new transition state with catalyst. And so now your energy diagram looks like this. So now, from where the reactants are to where your transition state is, this is your new activation energy right here, which is lower than the blue one. The blue one is uncatalyzed, the red one is with a catalyst. And so more of the collisions can reach or surpass this activation energy compared to this activation energy. And so that speeds up the reaction because your activation energy is lower. Same thing with an endothermic process. So instead of the transition state being so high, maybe it's here. So now this is your new pathway. And so the activation energy is this much compared to the blue one. So again, it changes the pathway, so your transition state is different, and so your activation energy is lower, so more of your collisions that normally would happen would be effective and cause a reaction. Here's some terminology that you need to be aware of. Catalyst is a substance that speeds up the reaction or the rate of the reaction without being consumed. That's a key here, without being consumed, because if I add more reactants, that will speed up the reaction, right? We talked about concentration increasing the rate of the reaction, but the difference here is that it does not get consumed. So you put it in and then you get it out. And it works by lowering the activation energy, just like we saw. There are homogeneous catalysts and heterogeneous catalysts. Homogeneous means the catalyst is the same phase as the reactants. So if all my reactants are solutions, then the catalyst is also a solution. Whereas a heterogeneous catalyst, also known as surface catalysts, these are in different phases. So maybe your reactants are solutions, but your catalyst is a solid, for example. So that's what this is saying here. Typically, the catalysts are solids, and the reactants are gases or aqueous. So the catalysis happens on the surface of the solid, and that's why they call it a surface catalyst. Acid-base catalysts. These are catalysts that involve the transfer of protons. We'll talk about more acids and bases in chapter 16 and 17, but in an acid-base reaction, protons are transferred. Enzymes are types of catalysts. They are macromolecules, big molecules that catalyze biological reactions. We call those enzymes. So not all catalysts are enzymes, but all enzymes are catalysts. So enzymes are a type of catalyst.